Now, we have to start. Now I would like to Tudor Dimofte, titled Free Manifolds and Quantum SL2C Connections.
Yeah, thanks very much. And thank you for the organizers. Thank you to the organizers for having this conference and for inviting me. I'd like to talk about some mathematical aspects of a project with Roland, Veen, and Davide Gaiotto. That it's been a long-standing project, or a long-running project that culminated in a very long paper this last May, which may be the first of several. The motivation and a lot of what we did, at least in this paper, was physical. The idea was, very briefly, to construct domain walls between four-dimensional supersymmetric quantum field theories. So, I have two 4D theories separated by some 3D domain wall on which the physics changes. And the reason this has anything to do with the present conference is because due to work of Witten and Gaiotto and Morenitsky, we know that there's a very nice class of 4D theories that are labeled by surfaces, by Riemann surfaces. Where somehow the physics and the theory is associated to the geometry of the surface. So, for example, we could have a theory on the left associated to some surface C1, and a theory on the right associated to some other surface C2. And then one may think, and it's in fact correct, that the natural domain walls between these two theories are labeled by three manifolds, in particular three manifold cobordisms between C1 and C2. So over here, there's some theory labeled by M, where M has boundary C1 and C2. Now, right, and so our goal was to write down these domain wall theories and understand their properties. And a very useful tool is a conjecture that I think first appeared several years ago in a paper of mine with Gaiotto and Lotte Hollands, sorry, with Gukov and Lotte Hollands, which was proved very recently by Cordova and Jaffers, which is that partition functions these theories labeled by three manifolds are in fact equal to partition functions of SL and C Chern-Simons theory on the three manifold itself. And for purposes of this talk, n is just going to be 2. So there's actually an integer on the left-hand side as well, which is just going to be 2. And I'll explain a little bit later that there are several versions of this correspondence. Roughly, Chern-Simons theory, complex Chern-Simons theory, has a complex level. So compact Chern-Simons, say SU2 Chern-Simons, has a real level k, and q to the 2 pi I over k is the thing that appears in the color Jones. Complex Chern-Simons has a complex level, sometimes written as k plus I sigma, where sigma is continuous and k is an integer. And so, at least naively, the types of things you can do on the right-hand side are labeled by an integer k. And indeed, the types of things you can do on the left-hand side are also labeled by an integer k. Namely, you take partition functions on the kth length space. So So this is some 3D theory which I haven't described and I'm not going to describe. It's some supersymmetric non-topological theory, which I'm going to compute its partition function on a length space. If that length space happens to be S2 cross S1, whether it's k equals 0, what I get is called a 3D index, or a superconformal index on the left. And that's precisely the kind of invariant that Stavros mentioned in his talk, as a 3-manifold invariant. And there's an S3 version 2, which I will also discuss, which is k equals 1 over here. And this is closely related to quantization in Teichmuller theory and to conformal blocks of Liouville theory.
Tudor?
Yes.
So the relation when k is 0 between sigma and q is?
And sigma. Right. So
Just for the audience.
So over here, but you never actually wrote down the 3D index. So for the index, there's a parameter q, which is e to the 2 pi over sigma.
Thank you.
It's an inverse level, but in this complex sense. Yeah, and there's going to be an h bar over here, which is some combination of 1 and the free variable sigma. Okay. Right, so the mathematical part of what we did was to try to find a nice way to understand and compute Trent-Simons partition functions for the relevant class of 3 manifolds. And in particular, we want to look at coordisms between punctured Riemann surfaces. I did not say punctured before, but punctures are actually very convenient here. So an example of the type of 3-manifold that arises is a complement of a trivalent graph. For example, here's S3. Let me draw a graph in it that looks like a tetrahedron. This 3-manifold topologically has a boundary that's a genus 3 surface. It's extremely convenient, like I have done, to take the surface and stretch it out into pairs of pants. And that pants decomposition is going to correspond to a choice of boundary condition for the Trent-Simons theory. Namely, it's a theory classically of flat connections, and to specify a flat connection on the boundary, I'll fix holonomies along all of the tubes. But as a cobordism, so this could very well be a cobordism between a genus 3 surface and nothing. But I can also interpret it as a cobordism between a 4-punctured sphere and another 4-punctured sphere, where I split the boundary into 2 halves, and I think of this as going from a 4-punctured sphere that looks like that to a 4-punctured sphere that looks like this, where again I'm drawing these pants decompositions. And so it changes the choice of pants decomposition. And very generally, well, the cobordisms we study include all changes of pants decompositions and mapping classifications one can implement on these surfaces. Okay, so the quantization problem here can be phrased roughly as follows. I'm going to introduce a little bit of geometry, not hyperbolic geometry, but flat connection geometry. That I'll try to connect to throughout the talk. So for the boundary of M, very roughly, one would like to associate a space of flat connections on the boundary. in this case, flat SL2C connections. Modulo gauge manifolds. It's a finite dimensional space, but it can have singularities. And it comes, at least on the smooth parts, it comes naturally with the Atiyah-Bott symplectic structure. It's a complex symplectic structure, which, if this means anything, is written as taking trace of variations of the connection, Wedgwood variations of the connection. If I, say, take a real slice of the space where I'm looking at SL2R flat connections instead of SL2C, and say I take positive coordinates, then I'm looking at Teichmuller space. And this thing, I think by work of Goldman and others, is the same as the Bay-Peterson symplectic form on Teichmuller space. So that's what I associate to the boundary. To the three manifold itself, I can associate a Lagrangian submanifold, ideally a Lagrangian submanifold, inside the space, which is roughly the set of flat SL2C connections that extend to the bulk. Okay.
Manifold, you just mean M, or?
I mean the interior of them. And so I will often say accidentally bulk instead of interior, but I mean exactly the same thing. Yes. So given this type of setup, the ideal outcome is to take this symplectic space and promote it to some quantum Hilbert space, where Hilbert, at least in this type, is going to be enclosed. And an algebra of operators acting on the space. So this is geometric quantization. Then the Lagrangian should define a wave function, z of m, living in the space, and by wave function I mean a vector. A vector living in the space defined, say, up to normalization. And this wave function is characterized by the property that it's annihilated by a set of difference operators, or just abstractly a set of operators that are a quantization of the classical Lagrangian equations. So it's a zero eigenvector of this operator. So that's okay. That's all very abstract, but I will make it hopefully a little more precise later. That is the general expectation. The main tool that we use in computing any of this involves ideal triangulations of these funny three manifolds. And by ideal, I just mean topological ideal triangulation. There are no hyperbolic metrics involved unless one wants them to be involved. By which I mean you can take a flat SL2C connection and try to write it as a hyperbolic metric, and then all of this makes sense in hyperbolic language. But if I'm just dealing with flat connections, everything is just topological. So this allows the Lagrangian and the phase space to be written as symplectic quotients of elementary things. So you can obtain them by taking a product of elementary Lagrangians and phase spaces associated to tetrahedra. Which are somehow canonical quantize these guys on each tetrahedron, and then do the symplectic reduction at the quantum level and pop out a quantum invariant. And so there's a whole machinery devoted to this, which I won't describe. I won't describe the machinery itself, developed by myself and a lot of other people over the past few years. Anyway, so what one gets at the end of the day, assuming this program works, and it does, is a quantum representation of the mapping class group of a punctured surface on some Hilbert space associated to that surface. And it's an infinite dimensional Hilbert space because we're doing SL2C rather than SU2. It's very closely related to the space that Francis talked about in his talk. I think it's probably some finite dimensional reduction or limit of what I will discuss. Okay. So this is the last part of this overview. Let me mention that there are many analogs between the SL2C invariants and more standard SU2 ones. So if I were doing SU2 Chern-Simons theory, the things I would talk about would be evaluations of quantum spin networks. So if I have my tetrahedral graph from over there, I can try to put a quantum spin network on it. Where each edge of the graph is labeled by some positive integer. And what I get, in general, I just have some trivalent graph, but for this particular graph, I get the 6J symbol, the quantum 6J symbol, for the Q of SL2. So what I mean by it here, and what mathematicians usually mean, I think, is the 6J symbol for finite dimensional representations of this at a rooted unity. But the key thing is finite dimensional representations. If instead I push through the SL2C story, I also get a 6J symbol for principal series representations of this. Principal series representations have continuous labels. Which are stuck on the edges of the graph. And in the geometric picture of flat connections, these continuous labels correspond to Holonomy eigenvalues that I fix on the tubes. So this 6J symbols, I think they were written down by Ponson and Teschner. And we find a kind of a nice intrinsically three-dimensional way to rederive them. This is what you get in the k=1 quantization. Okay, and both of these have volume conjectures. So I think most people here are familiar with the volume conjecture for SU2 Chern-Simons, Color-Jones, spin networks. In the SL2C case, it's even simpler, but the result is the same, and in fact the asymptotics should agree in the two cases. So in both cases, there's some quantum parameter that's sent to 0, such that the asymptotics of the partition function look like 1 over that small parameter times the volume of the manifold. And what I mean actually by volume of manifold, I mean volume of a flat connection. In this case, a flat SL2C connection. By which I mean the evaluation of the Chern-Simons action on that flat connection, which happens to be equal in the SL2C case to the standard volume cosine times the Chern-Simons.
What do you mean by
it's much easier to check and compute that this conjecture holds for the SL2C case. And in fact, it gives you a very easy way of computing what you think should be the asymptotics of the colored Jones.
There was a question?
Yeah, quantum spin network. So can you define the term quantum in this context? And what's spinning? Are you looking at a particle?
It's not, so it's not going to play any major role in this talk, but the analogy, if you're familiar with say, Jones polynomials or colored Jones polynomials, you have a knot, and you color it by a representation of SU2, and then you evaluate some brackets or some partition function that depends on that integer. And so there's a generalization of that to trivalent graphs, where now you label each edge of the graph by a representation of SU2, and in general, at the vertices, you have to give some kind of intertwiner that tells you how to connect the strands, but for SU2, that's unique. So there's no choice of vertices.
So what's the definition of spin in this context?
This representation is a spin.
Okay.
That's
The term.
yeah. So representations of SU2 are often called spin in physics. Cool. So the plan for the rest of the talk is to say a few more abstract things and then some concrete things. So I want to start off with what I'll call the quantum toolbox, or perhaps more appropriately, the quantum black box. I want to say what the input and output is of one of these quantization procedures. And then the second half, I want to describe why ideal triangulations and some extra structure on them leads to the right kind of input. So triangulated, and I often call them framed three manifolds. And then I'll give some examples of the kinds of partition functions one gets out of here, but hopefully the framework will be as interesting as the examples. Okay. Okay. So let me start. Again, I'm going to kind of think of quantization as a black box, taking some input and spitting out some wave functions in difference equations. And the way you do that depends on some integer k. Now, the input, I think most succinctly and also most abstractly, I can describe the input as a K2 Lagrangian submanifold of some phase space that has open patches that look like C star, look like complex tori. So C star to the 2D or some positive D. Okay, so let me unwrap that. What I actually mean, which is a little bit stronger than K2, though really just a little bit, is that I have some Lagrangian, C star to the 2D, that's obtained as a symplectic quotient, which again may be unfamiliar or very old terminology for this audience. So it's going to be a symplectic quotient of some tetrahedron Lagrangian, so product dependent of them, by n minus d, C star actually, where the tetrahedron Lagrangians are given by very simple equations. C C double prime plus C inverse minus 1 equals 0 inside C star squared, where C star squared is, well, it's C star squared, but nice coordinates on it are called CZ prime and C double prime, such that the product is minus 1. And it has a symplectic structure, dz over z, wedge dz double prime over z double prime. Okay, so what does this? And again, sorry for being extremely abstract at the moment. The C star, sorry, the quotient action is generated by n minus d monomial moments. Okay, so now let me go a step further. A geometric example of such a Lagrangian which I think initially started appearing in this language in Abhijit's thesis and in a paper by, well, a paper with an appendix by Nathan Dunfield. I think it was Boyd and yes, thank you. Good. So typical example is the A polynomial of a knot complement. The equation A of L and N, which is really A of L and N squared, equals 0, cuts out one of these Lagrangians in C star squared, which is the phase space associated with the torus boundary of the knot complement. And coordinates on this are L and M with a symplectic structure. Yes, with a symplectic structure, dl over L, wedge dm squared over m squared. The reason it works is due to Thurston's gluing equations on one hand, and the symplectic structure discovered by Neumann and Zagier, and later extended by Neumann on the other hand. So how do I form the A polynomial given an ideal triangulation? Let me cut the manifold up into n tetrahedra. The tetrahedra have edges labeled by shape parameters, usually called z prime and z double prime, which are equal on opposite edges and satisfy z prime, z double prime is minus 1, as well as the second equation, z double prime plus z inverse minus 1 equals 0. So from the view of just pure hyperbolic geometry, there's no difference between these equations. They're totally on the same footing. Though up here I've split them into kind of a phase space equation and a Lagrangian equation. Okay, we get the A polynomial by imposing gluing constraints on the tetrahedra. To glue, we set the product of shapes along every internal edge equal to 1. That ensures smoothness of the hyperbolic structure in the hyperbolic setting. And then to get, we also need a boundary identification. We need to know that the holonomies, the longitude and meridian holonomies on the boundary, are also products of disease. So these are eigenvalues of the longitude and meridian homonomies on the boundary of M, which is A torus. 2 cycles, two holonomial eigenvalues. So then we write down every equation on the board. We set mu j equals 1, just like I wrote, and eliminate everything except for but L and M. And we're left with a single equation, which is the A polynomial, or more precisely, some irreducible components of the A polynomial. This construction is tautologically the kind of symplectic reduction I wrote above abstractly, so long as the following is satisfied. If I think of the gluing constraints and L and M as functions on a space C star to the 2n, whose coordinates are just zi and zi double prime, and then there's a zi prime which is written in terms of those, ranging over all tetrahedra, with a symplectic structure that's just the sum of the tetrahedron symplectic structures I wrote here, or better yet, a Poisson bracket, such that log zi double prime log zj is delta ij, everything else vanishing, then the condition I need is that the mu j commute, they Poisson commute with each other. They Poisson commute with L and M. And that L and M, and these should all be, there are logs everywhere in these brackets. It doesn't matter for the ones that are 0. So let me write them in for the ones that are not 0. So log L, log M should be 1. Which is, as I just asserted, the right Poisson bracket for the boundary, the thing we expect for the phase space associated to the torus. It's the inverse of this symplectic. So that's the constraint. And this follows, these Poisson bracket relations follow from Neumann's idea for hyperbolic non-complements, and from Neumann for any 3 manifold with torus boundaries. Okay. So I think for the rest of the talk, I would propose to basically take this as the definition of what I mean by a K2 Lagrangian. I mean anything that comes from gluing equations that have these symplectic properties. Okay. So cool thing is that it works for non-complements, and it also works beautifully for the types of 3 manifolds that are, say, complements of trivalent graphs that I'll discuss. It also works for higher rank flat connections, if I want to consider SLNC rather than SL2C. And this was shown in work by Validis, Groner, and Zickert, and by myself with Maxime Gabella and Sasha Gunter. Once you have the algebraic structure there, you just need to fit everything into it appropriately. Okay. Now, that's the input. The output of quantization. Again, it comes in several versions labeled by this integer k. And each version has several different constructions that appear in the literature that are actually all equivalent to each other, though it's far from clear that that's the case, which makes the whole thing a little bit confusing. So let me summarize what's actually going on. I should say, so the various constructions of the same quantization are all the same, and they also, a cool thing that seems to be independent of K is that being able to define wave functions for some integrals or infinite sums, such that the integration contours or the sums converge, seems to depend on a positive angle structure. Being able for an actual manifold to have a positive angle structure on the triangulation, or abstractly to have the equivalent of that when I'm talking about case of Lagrange fields. So that became clear in, I think, work of Stradivarius and collaborators and Kashayev and Anderson. Okay, so here's, again, properties of the K equals 1 quantization. We have a phase space that looks like C star to the 2D. This gets promoted to a Hilbert space, and that looks like L2 of R to the V. One way to say what's happening is that we're quantizing a real positive slice. Where the coordinates are real and positive, or better yet, I take their logarithms and I insist that the logarithms are real. In other words, I do everything in terms of the logarithms and then exponentiate them at the end of the day. This Hilbert space for the boundary is the quantum Teichmuller space for the surface, if that means anything, or the space of Liouville conformal blocks. And just to give some references and names, so the 3D version of this, doing this quantization with tetrahedra, gives wave functions that can be computed in 2 ways. So one of them was described by Hikami, and then improved a bit by Kashayev and Anderson. And it's analogous to quantization of Teichmuller space in so-called Kashayev coordinates. And there's another way that I wrote about that's symplectically, which makes the symplectic reduction and the symplectic properties a bit more manifest, which is closely related to Fock-Chekhov quantization, which are equivalent. What you get for a tetrahedron is a wave function that depends on one of the tetrahedron variables. So there's a 2-dimensional space, but wave functions always depend on half of the variables. So you get something that depends on that, and a quantization parameter h bar. And so this z is, so the little z I wrote before is the exponent of this big Z I'm writing now. And this is a function that's basically the Barnes double gamma function, which was rediscovered by Fadeev as the quantum dilogarithm. The so-called non-compact version of the quantum dilogarithm. It can be written in many ways. One of them is an infinite product. It's an infinite product over R, 1 minus E, the R plus 1 H bar minus Z divided by 1 minus E to the R, 4 pi squared over H bar minus 2 pi I over H bar Z. So the numerator and denominator are related by sort of modular Jacobi transformation. Right, so this is quantum logarithm. It has two nice properties that I will list. One is the reason it's called a quantum dialog. If I take h bar goes to 0, this tetrahedron wave function looks like e to the 1 over h bar times a dialog, which is roughly a complexified volume for a tetrahedron. The other nice thing is that it's annihilated by difference operators. A difference operator and its dual, really. So they look like quantized versions of the Lagrangian equations. One of them looks like this. So z hat double prime plus z hat inverse minus 1 equals 0, where z hat is just multiplication by e to the z. So z hat inverse is multiplication, z hat inverse is multiplication by e to the minus z, and z hat double prime is a shift that sends the capital Z's appearing in the formula to z equals h. And there's a dual operator, which here will not play a major role, which is simply obtained by sending h bar to minus 4 pi squared over h bar and z to 2 pi I over h bar z. That's the sort of modular transformation. Okay. These properties then persist for any partition function one gets. And the general partition functions look like integrals of products of tetrahedron partition functions times some quadratic exponentials. And one can, at least in examples, and certainly try generally to work out the difference equations that annihilate these things, and they're quantized A polynomials. And in every example one has written down this way, you get the same quantum A polynomials that Stavros got.
So what are you integrating over in that expression?
I have made it incredibly vague. So it's because exactly what you do depends on how you label the tetrahedron. You're integrating over. So one way to write it is labeling the tetrahedron shapes as z1 up to zn, and then you're integrating over all the shapes. And then there's some quadratic exponential that involves some variable m, which is the logarithm of the n and the A polynomial. So you expect for a general 3 manifold, say for a knot complement, you expect that you get some wave function that depends on the meridian and h bar. Looks like that. It is a glorified Fourier transform.
But you're integrating over sort of all possible values of the zi, not like just the ones that are solutions to the Liouville equations.
Yeah, because the solutions for fixed n, the solutions of the Liouville equations are points. And so that's exactly, so conceptually what's going on is I'm doing quantum transaminase theory, which is not just about flat connections, but all connections. And it weighs them with some factor. And so if I want to interpret that as a quantum transaminase partition function, that's the factor that weighs a particular flat connection. I discretize the connection so that it's flat on tetrahedra but doesn't quite fit together right, and then I vary things and integrate the weight. And very briefly, there's the K equals 0 quantization, which is new and cool, and perhaps have a lot more done with it. So the K equals 0 quantization sends a classical space that looks like C star to the 2D to a Hilbert space that looks like L2 of S1 cross Z to the D copies of that. So this thing arose in work with Gaiotto and Coauthors on, as I said, 3D indices. And it was then studied by Gaiotto and collaborators. And let me just say the basic wave function here for a tetrahedron is also a sort of quantum dilogarithm. It depends on a phase, zeta, in other words, an S1 variable, and an integer m, and some quantum parameter q. And so it again has some infinite product form that looks like 1 minus q, the r, r plus 1 minus m over 2, zeta inverse divided by 1 minus q to the r minus m over 2, zeta. Which, unlike this expression, is a nice Q series and may have some relation to tails. Okay. That's it for quantization. Let me discuss some actual geometry and make it as light as I possibly can at the end of a long day.
So are we expecting to have k equals 2 and k equals 3?
We are, and I don't actually know formulas. I do know formulas for the corresponding physical things, and so one could presumably write down Boolean formulas. For general k, you get a vector space. The k equals 0 is special. For general k, the vector space looks like L2 of R tensored with a finite dimensional piece of dimension k. And so you expect the right kind of labels that work for that. Okay, so 3 manifolds. Let me define a class that I want to study. So topologically, I want 3 manifolds with boundary, such that the boundary is split into 2 different types of pieces. Which again is familiar, I think, in hyperbolic geometry. Right, but let me just say abstractly what's happening. So there's what I call the big boundary, which consists of punctured surfaces, or rather hold surfaces of any genus, such that the Euler character is negative. So 2g minus 2 plus the number of holes is positive. And these are the things that come up in Teichmuller theory, and they will come here as they come there with ideal triangulations. I will choose and fix ideal triangulations for these boundaries. Then there's small boundaries, which consist of disks, annuli or tubes, and tori, all of which would admit a Euclidean structure. Disks, annuli, and tori, such that the first two connect to the holes on the big boundary. So here are some examples. I should say, these guys get triangulated by ideal tetrahedra in 3 dimensions, and what I really mean by that topologically is a tiling by truncated tetrahedron. Which looks like this, such that the big faces are either glued in pairs, or they end up on the big boundary, like that. And the little faces, the truncated vertices, tile the small boundary. So, examples. Include a tetrahedron itself is a manifold of this type. The big boundary is a 4-punctured sphere, where I really mean a 4-poled sphere, and the small boundary consists of 4 disks, which simply fill in the holes at the vertices. Not complements. Are also of this type, that have no big boundary, and the small boundary is a torus. The complements of trivalent graphs that I started out discussing, let me draw another one. So this is the complement of a hop network. It's like the hop link with an extra bridge. This has a big boundary consisting of 2 3-punctured spheres. So the way I'm going to create these manifolds is by putting big 3-punctured spheres at all of the junctures that come with some ideal triangulations. And the small boundary consists of 3 tubes. Okay, that is the general idea. One can also come up with crazier things. Say, interpolating between a small boundary and a big boundary. So a cobordism that takes, well, so what I'm drawing is a solid torus, and from its core, I've cut out a big sphere and a tube, and then I can add another tube linking this core to the outer boundary. So the outer boundary is big. It has some ideal triangulation. I can cut it like this. And the inner boundary is one of these, is also a puncture torus, but an enhanced decomposition. So all of these work, and all of these are meaningful. So the 3D triangulations in the case of a single tetrahedron, or a not complement, well, the first one is obvious. The second one is Thurston, and then great generalizations. And right now is snacky. For these trivalent graphs, I think there's also a program called ORC that will at least try to do it. But there's a really cute and useful way to construct them from an elementary gadget. And the gadget is this. We're going to take a bipyramid. So take two two tetrahedra glued to each other along a face. This is the standard setup for the 2-3 move, but that's not what I'm going to do. And glue the front two faces kind of across the little boundary. So there's an identification here, and there's an identification here. I end up with a manifold that can be drawn somewhat more conveniently like this. You start with a solid cylinder and stick your fingers in at the ends until they touch. Get two conical ends on the inside connected by a tube. So this small tube in the middle is the small tube coming from the front of the picture on the left, whereas on the outside I have a big annulus with an ideal triangulation that looks like that. And so that's coming from the back of the manifold, and there are little disk boundaries here and here as well. Okay, so what can I do with this? Well, I can immediately create the torus example that I listed above. I just take this guy and rotate it around and glue the ends to themselves. So identify that with that. I'm not gluing any faces. I am just identifying this edge, and I get something that looks kind of like this torus cohort. I can then go ahead and take two copies of this and glue the big boundaries. Using an S transformation of the S element of the mapping class group, and I get the complement of the Hopf graph. I can do much more than build tori, so this thing, 4 of these guys can be put together in a circle. So I have 4. Where they connect, I get 3 punctured spheres. So each of these conical halves is half of a 3 punctured sphere. Then there are tubes that link them. And there are also some little tubes that go to the outside boundary. And then I collapse this solid torus into a 3-sphere in such a way that opposite tubes are identified, and this gives me, in a rather cool way, the complement of the tetrahedron graph. And I find that a pleasure to think about, though I'm not well at it further here. Okay, so let me say a bit about geometry. What do you do once you have one of these triangulations? The idea is to describe a boundary phase space that looks like some copies of C star and a Lagrangian submanifold that's obtained from the tetrahedron. And that needs 3 steps. So first I need a boundary phase space. So flat connections on the boundary. Then I need to look at flat connections in the interior. And then I need a map that takes the flat connection in the interior and restricts it to the boundary. In other words, I need to know how the coordinates are related. And then if all of the symplectic properties that I discussed at the beginning hold, I can plug this into the toolbox, into the black box, and quantize. So since time is a little bit short, I will say that all of the symplectic properties do hold, and this can be quantized. But the interesting part, and this slightly new part, I think mathematically, is how to define these coordinates. And this is related also to some work of Kabaya, and some things like this have also appeared in a paper by Bergeron, Faltel, and Liouville. Okay, so the key ingredient, which I should say is also heavily inspired by work of Fock and Gottschalk, is to study not flat connections, but framed flat connections. So let me say what that is. So first, let me say what a flat connection is. So I can consider a C2 bundle over a 3 manifold, typically just a trivial C2 bundle. Then a flat connection provides holonomy. It provides a way to transport the fiber over one point to the fiber over another point. So it provides parallel transport. The framing is going to be an extra choice of flat or invariant flag at each small boundary, or rather I should say on each small boundary. So for example, if I have a small tube, and I choose a flag on it, well, a flag in C2 is just a line in C2, which is a point on CP1. Locally, so this is, if I choose a flag in a fiber over a specific point, then I get a point in CP1. Now, I can do that at one point on a small boundary, and then I ask that it be invariant. In other words, that as I move it around, I parallel transport that line around and get back to itself, that the line is invariant. In other words, that line had better be an eigenline. So line is an eigenline of the flat connection. An eigenvalue, sorry, it's an eigenline of the holonomy of the flat connection. Okay, and so the reason that I defined the 3 manifolds this way to begin with, the reason that I specified what the small boundaries could be, and I didn't allow arbitrary genus, is because this condition is restrictive on arbitrary genus. But if the fundamental group of the small boundary is abelian, then this choice of flag is completely free. And given a flat connection, I can always find such a choice. The reason for doing this is twofold. It partially blows up. It partially blows up the moduli space and resolves singularities in the boundary space. And it allows a local definition of coordinates. So let me say what those coordinates are. Which it is, it's basically the only thing you can possibly do with a bunch of flags in a flag connection. Okay, So on a big boundary, they are basically Thurston's shear coordinates as kind of reinterpreted by Fock and Gauchois. So for every hole, there's a flag invariant under the holonomy around that hole. Sorry, and I should just say a line, since I'm working in C2. For every edge, there's a quadrilateral. So given an edge, E, there's a quadrilateral surrounding it, where there are 4 lines. We call them A, B, C, and D. The quadrilateral provides an unambiguous way to parallel transport the lines to a common point in the interior. Then they're all living in the same copy of C2, and I can take their cross ratio, and that cross ratio gives me an edge coordinate. Notice that it's invariant under rescaling of all the lines and also reparametrizing the basis of C2. And again, so these lines can also be seen as points in CP1, and if they're points in CP1, this is the standard cross ratio for points in CP1. So these are C-star coordinates associated to edges, and there's a Poisson bracket that Francis mentioned in his talk, which says that 2 edges that share a face are the only ones that have a non-trivial bracket. And it's plus or minus 1 for every face that they share, depending on orientation. Okay. Now, here's another rephrasing of things that are known. For a torus or annulus, for a small disk, nothing needs to happen. There's no coordinate associated to it, but one needs to remember that the holonomy around the disk is trivial, and so I need to say something else. So if I go along the big boundary and I try to compute an eigenvalue of a holonomy around one of the holes, lambda is equal to a product of minus xe coordinates for E around the hole. And that's squared. That's very easy to prove. Now, if one of these holes fills in a hole, then I better set that lambda equal to 1 and require unipotent holonomy. I cannot actually set from the boundary perspective in order to define this phase space. I can't specify that it's trivial, but I can specify that the eigenvalue is 1. Okay, so for a small torus or tube, there's always a non-trivial cycle, so I should say a cycle on a small torus or tube, gamma. I can try to find a holonomy eigenvalue. Well, I can just define it, sorry. So I can define the holonomy eigenvalue on gamma. And you might ask, which holonomy eigenvalue do I take? Well, there's a flag sitting on that small boundary. And the flag gives me a line in C2. It's an eigenline of the holonomy, and so I take the eigenvalue of that line. And finally, the most non-trivial part is that for tubes, I need a dual twist coordinate. And the way it works is the following. I again choose a path, or a homotopy class of paths along the tube. such that the path begins and ends in a certain triangle on the big boundary. There's a triangle there. There's a triangle here. These are, sorry, I should say these are analogs of Fenchel-Nielsen twists, but now in complex coordinates and talking about flat connections. The point, given such a path, I know that there's a flag or a line on the tube itself. I can parallel transport it freely everywhere along gamma. And there are two extra flags at the other corners of the triangles that this path connects. And I can use these to normalize F. So on the right-hand side, I can normalize F by multiplying it by S1 wedge S2, S1 wedge F, S2 wedge F. Where these are, I'm thinking of this as a line in C2, and so this is a determinant of the matrix formed by the two lines, and it's multiply that times F. That's a normalization, so this is a vector. No longer a line. And I can do the same thing on the other side. And then the twist coordinate is the ratio of normalizations. Okay. If I can have 5 more minutes. No, you don't. You want me to? Sorry. I can.
Well, yeah, 5 more.
I'll finish up. Okay. Sorry, that was probably too much detail. So, point is, on the boundary, I have coordinates xe for the big boundary. I have, say, longitude and meridian eigenvalues for tori. And I have eigenvalues and twists for the tubes. And the expected symplectic structure on this, the expected Poisson bracket, and one that corresponds to the Atiyah-Bott things on smooth parts of the moduli space, is that, well, I gave the one for the big boundary, the one for tori I also gave earlier, lm squared is equal to 1 in terms of logs, and now tau lambda is equal to 1 expected for the tubes. Okay, so the cool part is extending this to 3 dimensions. And roughly the idea is that for every tetrahedron, one can use, again, cross ratios of these lines to define what are effectively shape parameters. And so one gets UZ prime to double prime. They already obey from the perspective of the boundary. Because there's unipotent polynomial along the boundary, they already obey ZZ prime G double prime is -1. And in the interior, when taking these cross ratios, I can parallel transport them all. If I fill it in, I can uniquely parallel transport all 4 of the lines to the same point, and then there's a Kluger relation between the cross ratios, and it's the other tetrahedron equation. And I claim that defines some Lagrangian submanifolds. And then there are simple monomial relations, which anyone who's interested can find in our paper. Between the shape parameters here and the boundary coordinates. And so one just glues up the manifold as usual then. And the claim is that they actually satisfy all the symplectic properties that I described in the beginning. So, great. Let me give you an example of what one actually gets out of this. One can take the picture I had before of a cobordism between a Pans-decomposed torus and a big boundary torus. So it's a cobordism between this and like this. On each side independently, one can compute holonomies on the left, and one can simply define boundary coordinates lambda tau on the left, and some edge coordinates xx prime, x double prime on the right. But the three manifold gives the relation. So the Lagrangian for the three manifold in this case involves relations such as lambda plus lambda inverse is something like 1 over x prime square root plus square root of x prime plus square root of x over x prime minus. Which is actually a relation that came up in Francis's talk. So this is a three-dimensional way through tetrahedra of expressing the trace of the holonomy in a path decomposition in terms of edge coordinates on the other side. And the wonderful thing is that there's a unique way to quantize this, sprinkle in factors of q, and get a wave function associated to that cobordism for, say, quantum Teichmuller theory. And then for the other manifolds, one gets the S transformation of the puncture torus, or this 6J symbol for multiple series representations of UQSL2 or so on. Thanks. Sorry about I would not, but only because they're incompatible with the quantization. So they're incompatible with having, so the quantization wants some kind of positive angle structure on the whole thing. And in particular, it wants the small boundaries to be Euclidean. And I need to make that much more precise, but I can't right now. There's no problem with spheres classically, but you can't quite quantize them. They seem to violate some